Hello all, my name is Joel Padgett and thank you so much for joining me today. I'm delighted to share with you an ongoing research project investigating the spatial and temporal distribution of neotectonic activity in the Araya-Paria Peninsula. So, the Araya-Paria Peninsula is located in the southeast Caribbean along the active plate boundary between the Caribbean plate and the South American plate, right along the northern coast of Venezuela. The Caribbean plate migrates at about 20 millimeters per year east relative to the South American plate, and the majority of this motion, about 18.5 millimeters per year, is accommodated by the dextral El Pilar strike-slip fault, which you can see in Figure 1, this white line here. Current research suggests that deformation associated with this active plate boundary has resulted in a releasing bend forming a pull-apart basin in the Gulf of Paria, which is in the east-south side of the study area. And it's currently hypothesized that the Paria Peninsula in the east is subsiding east end down into the Gulf of Paria pull-apart basin. For this study, we looked to test that hypothesis and then expand the study area to the rest of the Araya-Paria Peninsula to understand how plate deformation is partitioned on quaternary timescales. To do this, we used a DEM, a 30-meter DEM, to identify 175 catchments across the peninsula. We calculated the hypsometric index, the valley width to height ratio, the catchment asymmetry factor, and the catchment elongation index for each catchment, and then we calculated the mountain front sinuosity index for 119 fronts across the study area. And what these indices allow us to do is quantify the relationship between tectonics, climate, and surface processes shaping a landscape, and we controlled for climatic and surface processes to allow us to understand the role of tectonics in shaping the landscape and use that information to understand how plate deformation is partitioned across the region. So we calculated the mountain front sinuosity index, with red mountain fronts being the most planimetric recently uplifted, and yellow representing the most sinuous, more mature mountain fronts that have been highly eroded. We see the most sinuous mountain fronts in the south side of the Paria Peninsula in the east, and we see the most planimetric mountain fronts in the south-central region of the study area along the plate boundary and in the western Araya end of the peninsula. We also calculated the hypsometric index, and there's a general eastward increasing in HI, though there were three distinct zones, a wide range of values in the Araya Peninsula, a narrow range of values in the central area of the peninsula, and a wide range of values in the eastern Paria. Valley width to height index is a measure of how V-shaped or U-shaped valleys are. The majority of these valleys are V-shaped or U-shaped, so they're fairly well eroded, with the exception of a few key spikes around 600,000 meters easting and 450,000 meters easting. This is the catchment asymmetry index for the Paria portion of the peninsula. It's been hypothesized that there's east side tilting into the Gulf of Paria. If that were the case, we would expect to see a fairly uniform direction of catchment asymmetry, as indicated by these arrows, but as you can see, the arrows sort of point in all directions, suggesting that there was no uniform direction of tilt toward the east. So we identified three distinct tectonogeomorphic zones: the Araya zone in the west, the central zone in the center, and the Paria zone in the east. In the Paria zone, we see sinuous and drowned mountain fronts, elongated southern catchments, a wide range of HI values, and a non-uniform direction of catchment asymmetry, which we interpret to indicate whole block subsidence in the east with a component of south side down tilting. In the central zone, we see a drainage reorganization and catchments elongating east-west rather than north-south and draining east-west rather than north-south. We see planimetric mountain fronts, particularly along the active plate boundary. We see a narrow range of HI values and a fairly sharp increase in valley width to height ratios, which we interpret to be the result of dextral compression resulting in internal dip-slip partitioning in the central zone. In the Araya zone, we once again see north-south draining catchments, a wide range of HI values, and on the boundary between the central and Araya zones, we see generally low elevation relief and highly denuded mountain fronts, and moving west we see more planimetric mountain fronts and low width to height values, which we interpret to suggest dextral tension resulting in regional subsidence in the eastern Araya with a minor component of dip-slip partitioning in the west. I'd like to thank Dr. Jenny Arkle and Dr. John Weber for their invaluable time and expertise, and my colleagues in the Augustana Geology Department. Thank you so much, and I hope you have a great afternoon.